You begin by noticing the ground beneath you, even if you are lying in a bed, even if you are wrapped in blankets, even if your eyes are already half closed. Beneath the floor, beneath the walls, beneath the quiet structures of human making, there is stone. And beneath that stone, there is older stone. And deeper still, there is warmth, and motion, and time moving at a pace so slow it feels like stillness. You do not need to imagine fire or danger. Tonight, you imagine breathing. The earth beneath you is not a cold, dead sphere. It is warm-blooded in its own geological way. It releases heat from its birth, leftover energy from when the planet first gathered itself from dust and gravity. That warmth has never fully faded. It travels upward in patient currents, like heat rising through a sleeping body. You are resting on the skin of something vast. If you could shrink yourself down to the thickness of a grain of sand compared to an apple, that thin layer would be the crust, the outer shell where oceans sit and mountains rise and forests grow. Nearly everything you have ever touched lives on that delicate layer. And yet beneath it lies a deep interior that moves slowly, like thick honey warmed by the sun. In some places, that slow movement gathers and waits. These places are not always marked by tall cones or smoking peaks. Some of them are wide and quiet. Some look like valleys. Some hold lakes. They do not announce themselves loudly. They do not demand attention. They are known as supervolcanoes, though the word super speaks only to size, not temperament. You can think of them as deep chambers where melted rock, called magma, collects far below the surface. Not rushing, not boiling like a pot, but resting in long preparation, held under pressure, insulated by miles of solid stone. Magma is simply rock that has become fluid from heat and pressure. It is not separate from the earth. It is earth, transformed. Like ice becoming water, like water becoming vapor, it is a change of state, not a change of identity. And these magma reservoirs can be enormous, stretching across tens of kilometers, shaped like uneven bowls and branching pockets. They do not fill quickly. They gather slowly across thousands, sometimes hundreds of thousands of years. A drop added to a drop added to a drop, across ages longer than human memory. You might imagine a lung taking a very long breath. Supervolcanoes are defined by the scale of what they could release if they ever fully erupt, more than 1,000 cubic kilometers of material. It is a number so large it becomes abstract, so you let it soften. You picture landscapes reshaped, not in violence, but in magnitude. Nature working with large brushes instead of small ones. But tonight, you are not here for eruption. You are here for presence. Most supervolcano systems spend the overwhelming majority of their existence in quiet states. They cool. They crystallize. They shift slightly. They rest. Even when magma is present, it is often partly solid, like a frozen drink beginning to melt again at the edges. Scientists call this a crystal-rich mush, not a chamber of liquid fire, but a textured mixture of melt and mineral. This is important. Stillness is common. Catastrophe is rare. You can feel your shoulders soften a little more as you hear that. Above some of these deep systems, the ground forms a wide depression called a caldera, a basin-shaped hollow created long ago when the surface collapsed after a massive eruption emptied space below. Over time, water may fill it. Sediment may smooth it. Forests may grow inside it. Life returns easily to old scars. If you have ever seen a large, round lake surrounded by gentle slopes, you may have been looking at the quiet surface expression of something once unimaginably powerful and now deeply asleep. The planet is not hiding danger from you. It is holding history. And history, in geology, moves with a slow heartbeat. One pulse may take 10,000 years. Another may take 50,000. The intervals are long enough that worry has no useful foothold. Instead, there is only curiosity, the calm curiosity of listening to something older than language. You are not separate from this planet. The iron in your blood was forged in ancient stars. The calcium in your bones once traveled through stone and sea. When you place your attention on the ground, you are not reaching outward. You are remembering connection. Supervolcanoes are not villains in this story. They are chapters. They participate in cycles that shape continents, renew soils, and alter climates across deep time. Their eruptions, when they happen, are part of Earth's long conversation with itself, a conversation conducted through pressure, temperature, chemistry, and motion. And like any deep conversation, it leaves signals. Long before any major eruption, the Earth begins to adjust. Rock bends slightly. Tiny fractures form. Heat shifts pathways. Gases change their routes. The planet does not act without whispering first. It speaks through subtle changes, too small for human senses alone, but not too small for careful instruments. So you begin to sense a comforting truth. You are not standing above a mystery without listeners. All around the world, scientists place gentle tools against the Earth, devices that feel vibrations, measure distances, detect warmth, and sample invisible breath. They do not wait for catastrophe. They listen continuously, like night watch keepers beside a sleeping giant. Listening is the central act. Not fearing. Not guessing. Listening. You imagine placing your ear against the chest of the planet and hearing slow rhythms, movements measured in millimeters, pulses measured in microquakes, breaths measured in molecules. The signals are faint, but they are faithful. The Earth is never truly silent. Only very, very soft. And as your own breathing slows, you begin to wonder if the ground is always speaking in tiny motions and quiet waves. How exactly do we learn to hear its hidden language at all? You let your mind drift into the idea of size, but gently, without numbers at first. You imagine holding a single grain of sand between your fingers. It is small enough to disappear if you blink. Now you imagine a beach made of these grains, stretching beyond your sight. Then a coastline. Then a continent. Your thoughts widen step by step, not to overwhelm you, but to stretch your sense of scale like a slow, comfortable breath. Science often begins this way, not with equations, but with comparison. When you hear the word volcano, you might picture a mountain with a peak, a plume, a glowing ribbon of lava tracing down its side. This is a familiar image. A contained image. A volcano that stands like a chimney, releasing pressure from a focused point. A supervolcano is different in shape, but not in nature. It is not always a mountain. Often, it is too wide to see all at once. It spreads beneath the surface like a great underground lake of softened rock, its roof made of many kilometers of solid crust. Instead of a chimney, it is more like a vast ceiling with many tiny cracks and pathways. The word super does not mean more angry. It means more spacious. You can think of eruptions size the way you think about containers. A teacup can spill. A bathtub can spill. A reservoir can spill. The behavior is similar, but the volume changes the consequence. Scientists classify eruptions partly by how much material is released: ash, rock, gas, and molten fragments, and the highest category belongs to the rarest, largest releases in Earth's history. These are called supereruptions. But you stay with calm imagery. You imagine a snow globe. When shaken, a small globe fills with swirling flakes for a moment. Now imagine a globe the size of a stadium. The same motion would carry far more snow, drifting much longer before settling. The motion is not harsher, only larger. Beneath a supervolcano lies a magma reservoir, sometimes called a magma chamber, though the word chamber can be misleading. It is rarely an empty cave full of liquid. More often, it is a sponge-like region of hot rock containing pockets of melt between crystals, part solid, part fluid, part evolving. A glowing mosaic instead of a pool. You picture warm caramel with grains of sugar still inside. Not fully melted. Not fully firm. Pressure builds there slowly. Rock above presses down with enormous weight. Heat from below keeps minerals near their melting point. New melt may rise from deeper layers and join the system. Gas is dissolved in the melt. Water vapor, carbon dioxide, sulfur compounds remain trapped by pressure, the way bubbles stay hidden in a sealed drink. Pressure in geology is not panic. It is patience. It increases grain by grain, year by year. Most of the time, it also releases grain by grain, through tiny cracks, minor intrusions, and gradual cooling. Balance is common. Dramatic imbalance is rare. This is one of the most comforting truths in volcanic science: the extremes make headlines, but the norms make reality. You explore the idea of volume again, this time with stone. Imagine carving a cube 1 kilometer wide, 1 kilometer long, and 1 kilometer tall. Now imagine 1,000 of those cubes. That total volume defines the lower threshold of a supereruption's output. Your mind does not need to hold the full picture. It only needs to recognize that nature sometimes works on scales far beyond daily life. And yet, even these systems are built from small processes repeated. Tiny melt fractions gathering. Minute temperature changes. Crystal structures forming and melting again. The extraordinary grows from the ordinary, given enough time. This is a soothing pattern you see throughout science, complexity emerging from simple rules applied patiently. You might wonder why magma gathers in some places and not others. The answer lives in plate tectonics, the slow motion of Earth's crustal plates floating on the warmer, softer mantle below. Where plates stretch apart, melt can rise. Where one plate sinks beneath another, water lowers melting points and creates magma. Where crust is unusually thick and warm, melt may collect and linger. A supervolcanic system often forms where heat supply, crustal structure, and time align like three quiet notes forming a chord. Time is the longest note. Some magma reservoirs evolve over hundreds of thousands of years. During that span, melt may enter, cool, crystallize, and remelt many times. the system changes shape. It migrates slightly. It breathes in slow geological cycles. If you compare it to weather, it is not a storm but a climate, persistent, layered, gradual. You are invited to release the idea of suddenness. Even when large eruptions occur in Earth's history, they are usually preceded by long preparation phases. Rock does not surprise itself. Physics is consistent. Heat moves according to rules. Pressure follows pathways. Signals appear for those who know how to listen, and listening is exactly what modern monitoring is designed to do. But before listening comes measuring. And before measuring comes defining. Scientists needed a scale to compare eruptions across time, so they created one, the Volcanic Explosivity Index, or VEI. You can think of it like a staircase where each step represents roughly 10 times more erupted material than the last. It is logarithmic, like the way sound volume increases in steps rather than straight lines. Small eruptions sit on the lower steps. Historic large eruptions sit higher. Supereruptions stand at the top step, VEI 8, not common, not expected, but recognized as part of Earth's long story. A scale does not create fear. It creates clarity. They help observers stay organized and calm. They turn mystery into method. You return again to the feeling of lying above deep time. Beneath you are layers of rock, beneath them zones of heat, beneath them slow currents carrying energy outward. Somewhere in the world right now, magma is cooling into crystal. Somewhere else, crystal is warming toward melt. The planet is always in transition, but rarely in crisis. And now a softer question begins to form. If size can be defined, and pressure can be estimated, and systems can be classified like stars in the sky, what delicate instruments allow humans to sense the smallest motions inside something so enormous and so deep? You begin by listening, not with your ears, but with your imagination. You picture the ground beneath you not as silent, but as softly expressive, like a sleeping creature that shifts its weight from time to time. Not suddenly. Not violently. Just enough to remind you that stillness is often full of motion too small to feel. The earth is always moving. Most of this movement is far below your senses. Your feet cannot detect it. Your skin cannot register it. But sensitive instruments can, devices so patient and precise that they notice motions smaller than the width of a human hair. Through them, the planet speaks in vibrations, and scientists learn to listen like careful translators of a subtle language. This language is called seismic activity. The word seismic comes from an ancient term for shaking, but tonight you think of it more like trembling, the way a leaf trembles when a faint breeze passes through. The ground trembles for many reasons. Rock shifts along fractures. Magma adjusts position. Fluids move through cracks. Pressure redistributes itself like weight settling into a cushion. Each motion sends out waves. Not ocean waves, not sound waves through air, but elastic waves through rock, pulses of energy that travel outward in all directions. You imagine dropping a pebble into a still pond and watching rings expand across the surface. Seismic waves move in a similar pattern, except the pond is solid stone, and the rings travel invisibly through the planet itself. There are different kinds of these waves, and you meet them like different musical notes. The first are called primary waves, or P waves. They are the fastest travelers, compressing and expanding the rock as they pass, like a gentle squeeze and release. They can move through solids and liquids alike. You imagine them as the first quiet knock on a distant door. Next come secondary waves, or S waves. They move more slowly and only through solid material, swaying the rock side to side. If P waves are a squeeze, S waves are a sway, a subtle rocking motion passing through deep layers. Later still come surface waves, rolling along the outer layers like slow ripples across a field. These are often the waves people feel most strongly in earthquakes, but in volcanic regions they are often very small micromotions, soft signatures, geological murmurs. To detect these whispers, scientists use instruments called seismometers. You can think of a seismometer as a stethoscope for the planet. It rests against the ground and listens continuously. Inside is a carefully suspended mass that prefers to remain still. When the ground moves, the casing moves with it, but the mass lags slightly behind due to inertia. That tiny difference is recorded and translated into a signal, a line that wiggles across a digital page. A wiggle becomes a word. A pattern becomes a sentence. Modern seismometers are incredibly sensitive. They can detect vibrations from distant earthquakes across the globe, storms crashing on faraway coastlines, even large ocean waves transferring energy into the crust. But in volcanic monitoring, scientists are especially interested in local patterns, repeated small signals clustered in one area. These are called microearthquakes. The word earthquake might sound too large for such small motions, so you soften it in your mind. Think of them as rock adjustments. Stress release ticks. Structural size. When magma moves or pressure changes underground, surrounding rock responds. It cracks microscopically. It slips slightly. Each slip sends a tiny wave outward. One tiny signal alone is like a single syllable. But many signals together form a conversation. You imagine a quiet control room somewhere near a wide volcanic caldera. Screens glow softly. Lines scroll slowly across displays. Each line traces ground motion in real time. Most of the time, the lines are nearly flat, with only delicate texture. Occasionally, a cluster of small wiggles appears, not alarming, just noteworthy. Like hearing a sleeping person turn over and settle again. Patterns matter more than single events. If microquakes begin to occur more often, or migrate upward, or align along a path, scientists take interest. Not fear, interest. Because movement pathways can suggest where fluids or melt are traveling. The Earth leaves breadcrumbs, and seismic monitoring is one way of seeing the trail. Some signals are even more distinctive. In volcanic regions, there is a special kind of vibration called harmonic tremor. Instead of sharp spikes, it appears as a steady, humming signal like a continuous musical tone. It often indicates fluid movement, such as magma or gas flowing through channels underground. You picture it as a low cello note played beneath the surface. This does not automatically mean eruption. It means motion. And motion is information. In science, information is calming because it replaces guessing with observing. The more clearly you can observe, the more gently you can respond. Networks of seismometers are often placed around known volcanic systems, spaced like listening posts. By comparing arrival times of waves at different instruments, scientists can locate where a vibration began, much like your brain locates sound by comparing what each ear hears first. Location turns noise into a map. Over time, these maps reveal active zones, regions where rock frequently adjusts, where fluids circulate, where pressure interacts with structure. The map is never final. It evolves like weather patterns, like constellations slowly shifting over centuries. You rest with the idea that the planet is not hiding its motions. It is broadcasting them constantly, softly, faithfully. And yet, interpretation is an art as well as a science. Not every tremor means the same thing. Not every cluster signals change. Some are caused by groundwater movement. Some by cooling rock contracting. Some by distant tectonic stresses passing through. The language is real, but it has dialects. Your breathing grows slower as you picture this: a planet speaking, instruments listening, humans learning patiently. No rushing. No guessing. Just attentive translation of tiny waves traveling through deep stone. And a gentle curiosity begins to form in you now. If vibrations reveal motion, what might the slow lifting and sinking of the land itself quietly reveal next? You let your awareness rise now, as if your perspective is slowly floating upward like a feather in calm air. You are still connected to the ground, but you are no longer pressed against it. You are hovering gently above hills, valleys, plains, and wide volcanic basins, seeing the land not as frozen scenery, but as a surface capable of subtle motion. At first, it looks completely still. Mountains appear anchored. Plateaus appear permanent. Valleys seem carved and finished. But science teaches you a softer truth: the land is not rigid like glass. It is more like thick fabric stretched over a warm, shifting frame. It can lift slightly. It can sink slightly. It can tilt by amounts so small that only instruments notice. This slow changing of shape is called ground deformation. You can think of deformation as posture change. When you inhale, your chest rises a little. When you exhale, it settles. The movement is gentle, rhythmic, alive. In certain volcanic regions, the Earth's surface behaves in a similar way when magma or heated fluids move underground. Pressure increases, and the surface may arch upward by a few millimeters or centimeters across a wide area. A few millimeters sounds like almost nothing. And for your daily life, it is. But for measurement, it is a sentence written clearly. Imagine placing a loaf of bread in the oven and watching the dough slowly dome as warm air expands inside it. The crust lifts not because something breaks, but because something grows warmer and more spacious beneath. Volcanic uplift can behave like that: not a crack, but a curve. To observe these curves, scientists use networks of high-precision GPS instruments fixed to the ground. These are not the simple navigation receivers in phones and cars. These are geodetic GPS stations, deeply anchored, continuously recording, exquisitely careful. They listen to multiple satellites at once and calculate their position to within a few millimeters. You imagine them like quiet hikers standing perfectly still, noticing the horizon shift. Each station reports its position day after day, night after night. Alone, one station tells a tiny story. But many stations together tell a landscape story. If several slowly move apart, the ground between them is stretching. If they move closer, the ground is compressing. If they all rise slightly, the land is lifting like a slow tide. Nothing needs to be guessed. Position becomes evidence. You might picture a giant invisible grid laid across the Earth, with certain points pinned and watched with devotion. Over weeks and months, scientists compare coordinates and see motion drawn as delicate arrows. Most arrows are very short. That is comforting. It means the planet prefers gradual adjustment. But GPS is only one way of seeing shape. There is also radar from space, a method so elegant it feels almost like poetry. Satellites orbit high above, sending radar pulses down toward the surface and measuring how long they take to return. When repeated over time, these measurements can reveal changes in elevation across entire regions. This technique is called INSAR, interferometric synthetic aperture radar, but you let the long name soften and pass. You keep the image instead. A satellite sending gentle taps of energy. The ground answering back. By comparing the returning signals from different dates, scientists can detect whether the land has moved closer or farther away by just a few millimeters. The results appear as colored contour patterns, rings and bands like fingerprints or tree rings, each shade representing a tiny vertical change. It is like watching the Earth breathe in color. From space, uplift often appears as a broad, smooth dome centered over an active underground system. Subsidence, the opposite motion, appears as a shallow bowl where ground settles after fluids leave or rock cools and contracts. These patterns are rarely sharp. They are gradual gradients, like slopes of light. You rest with the idea that swelling land is not automatically a warning. Often it is simply adjustment, magma entering a reservoir, hydrothermal fluid shifting, pressure redistributing through porous rock. Motion is not catastrophe. Motion is communication. Scientists look not just for uplift, but for rate. Speed matters more than shape. A change of 2 centimeters across a year is different from 2 centimeters across a week. Time turns measurement into meaning. So records are kept patiently. Months become baselines. Years become context. Each volcanic region develops its own deformation personality, a typical background rhythm of tiny ups and downs. When new motion differs from that rhythm, curiosity awakens. Instruments are checked. Other signals are compared. Listening becomes more focused, but still calm. You imagine layers of observation overlapping like transparent sheets, seismic vibrations, gas measurements, heat flow, and now ground shape. No single layer tells the whole story. Together, they form a fuller picture, like chords instead of notes. Even temperature changes can cause slight deformation. When rock warms, it expands. When it cools, it contracts. The effect is small but measurable across large areas. The crust behaves less like ceramic and more like slow memory foam, responsive, not brittle. Stillness, you realize, is often motion spread across time. You let that thought settle into you. Many things that feel unmoving are simply moving slowly beyond perception, continents drifting, mountains eroding, magma migrating grain by grain. Your own body replaces most of its atoms over the years, yet you feel continuous. Change does not always announce itself. From above, with satellites and stations and patient mathematics, the Earth's posture can be read like body language. A lift here. A tilt there. A widening arc across a caldera floor. None of it loud. All of it informative. And as you float in this high, gentle perspective, another curiosity forms: if the ground can rise and fall from hidden warmth below, how might that hidden warmth itself be sensed and mapped in the dark? You bring your attention now to warmth, not the warmth of a flame, not the flash of fire, but the deep, steady warmth that lingers in places where energy has been resting a long time. Like a stone that has held the day's sunlight and releases it slowly into the evening air. Like your own hands when they are folded together beneath a blanket. Beneath your feet, warmth lives in the rock. The earth carries internal heat from several sources. Some of it is ancient leftover energy from the planet's formation, when countless collisions and compressions generated tremendous temperature. Some of it is continuously renewed through radioactive decay, where certain elements release tiny packets of energy as they transform. None of this is violent. It is quiet and constant, like a long burning candle deep inside a sealed lantern. In volcanic regions, this warmth sometimes gathers closer to the surface. Not as rivers of fire, but as elevated temperature gradients, places where rock is a little hotter than its surroundings, where underground water circulates and carries heat upward, where magma bodies slowly cool like buried embers. These zones create thermal fingerprints, and with the right tools, those fingerprints can be gently read. You imagine heat as a whisper that travels through contact. Scientists measure underground heat in several calm ways. One method is direct placing temperature probes into boreholes, which are narrow drilled openings in the ground. These probes sit quietly and record temperature over time. They do not disturb. They simply notice. Over months and years, they reveal whether warmth is stable, rising, or fading. A changing trend matters more than a single number. Another method is indirect and elegant, watching how heat changes the behavior of water. Warm rock heats groundwater. Heated groundwater rises, circulates, dissolves minerals, and sometimes emerges at the surface as warm springs, steaming vents, or altered soil. You may have seen places where snow melts first in small patches on a hillside. Often, hidden warmth is working there from below. These are Earth's warm breaths. Thermal areas around volcanic systems are often called hydrothermal fields, hydro for water, thermal for heat. You picture them as underground plumbing networks, where water moves through cracks and pores, carrying energy like a messenger. When the heat supply changes, the water's pattern changes too. Temperature shifts, flow speeds adjust, mineral content varies. So by studying water, scientists study heat. But there is also a way to sense warmth without touching the ground at all. You rise again in your imagination, drifting upward above clouds, above weather, into the calm pathways where satellites circle the planet. Some of these satellites carry thermal infrared sensors, instruments that detect radiation associated with temperature. Everything warmer than absolute zero emits infrared energy. Even you. Infrared cannot be seen by human eyes, but sensors can translate it into images where temperature differences appear as shades and colors. From orbit, these instruments map the subtle glow of the Earth's surface. Most places change temperature with sunlight and shadow, day and night. But geothermal areas often remain consistently warmer than their surroundings. Consistency becomes a clue. You imagine a nighttime satellite pass over a volcanic caldera. The land has cooled after sunset, but certain patches remain slightly warm: thin lines, soft pools, scattered spots. These are not fires. They are heat leaks, gentle and persistent. Over repeated passes, scientists compare images and look for change. Expansion of a warm area can suggest shifting underground flow. This is not dramatic watching. It is patient watching. Thermal monitoring is especially useful because heat often moves before rock does. Temperature changes can precede deformation. Warm fluids may rise before ground lifts. A system may redistribute energy quietly long before it redistributes mass. In this way, heat is sometimes an early storyteller. You think of placing your hand near a closed oven and sensing warmth before you see what is cooking inside. There are also airborne surveys instruments mounted on aircraft or drones that fly careful patterns over geothermal regions. They measure surface temperature with fine resolution, creating detailed thermal maps. These flights are like gentle scans, reading the landscape's invisible glow. No single warm spot means danger. Warmth is natural in many geological settings. What matters is deviation, warmth appearing where it was not before, or increasing beyond its long-held pattern. Change over time is the true signal. Patterns are the lullaby of science. You rest into that idea that repetition brings understanding. A single measurement is a note. A long record is a melody. Scientists build melodies of data, stretching across seasons and years, so that when a new note appears, it can be heard in context. Heat also changes the chemistry of rock. Warmer conditions alter minerals, creating new compounds, new colors, new textures. Around volcanic systems, you sometimes find bright mineral deposits, yellows, whites, reds, painted by chemical reactions driven by heat and fluid. Mapping these alteration zones helps outline where thermal energy has traveled. It is like seeing where warm hands once rested on cold glass. Even gases carry thermal information. Warmer systems release different gas mixtures than cooler ones. The ratios shift subtly. Instruments detect these differences and add them to the growing portrait. Each method, temperature probes, satellites, water chemistry, gas sensors, contributes a brushstroke. No single brushstroke makes the painting. You breathe slowly and imagine the underground not as a furnace, but as a network of warm currents, pockets, channels, gradients, all moving at speeds that make no demand on your nervous system. Geological heat is unhurried. It prefers centuries to seconds. And because it is unhurried, it can be watched. Warmth, you realize, is one of the planet's most honest signals. It does not hide well. It seeps, glows, transfers, reveals. And as this gentle inner glow continues its slow journey upward through stone and water, another softer curiosity begins to form. If heat can travel and be traced, what invisible breaths might be rising with it into the air above? You settle into the idea that the earth does not only move and warm, it also breathes. Not with lungs, not with ribs and airways, but with pathways and pores and fractures in stone. Gases travel through these tiny routes, rising slowly from depth toward the open sky, like thoughts floating up from a dreaming mind. Most of this breathing is invisible. You walk across it without noticing. You sleep above it without sensing. And yet, in volcanic regions especially, the ground releases small amounts of gas continuously, a soft exhalation from chemical reactions and heated materials far below. This is not unusual. It is part of how pressure balances itself gently over time. You imagine the crust like a thick blanket, and gases like warmth finding its way through the weave. The most important volcanic gases include water vapor, carbon dioxide, and sulfur dioxide. Water vapor is the most abundant, simple steam, familiar and gentle. Carbon dioxide is heavier than air, colorless, odorless, a natural part of the atmosphere and of your own breath. Sulfur dioxide has a sharper personality. It carries a distinctive scent, like struck matches, even in small amounts. None of these are villains in themselves. They are messengers. Deep underground, magma contains dissolved gases, held in place by immense pressure. You can picture a sealed bottle of sparkling water. When the bottle is closed, the gas stays dissolved. When the cap is loosened, bubbles form and rise. In a similar way, when pressure changes underground, gases separate from melt and begin traveling upward through cracks in porous rock. This separation is called exsolution, a quiet unmixing. Even when magma remains deep and mostly still, small amounts of gas can escape over long periods. These gases seep through soil, enter groundwater, emerge in fumaroles, which are warm gas vents, or diffuse invisibly across wide areas. The flow is often slow and steady, like a long sigh. Scientists monitor these gases because changes in composition or flow rate can signal changes underground. You imagine gentle instruments placed near vents and warm fields, not loud machines, but careful tasters of air. Some draw in samples and analyze them directly. Others use laser-based sensors that measure gas concentration from a distance by observing how specific wavelengths of light are absorbed along a path. Light passes through air. Air leaves a signature. Each gas absorbs light in its own pattern, like a barcode. Instruments read that pattern and calculate how much of each gas is present. It is a quiet kind of reading, no drilling, no digging, just watching how invisible molecules shape passing light. There are also mobile measurements. Scientists sometimes walk survey paths with handheld detectors, or mount sensors on vehicles and drones, mapping how gas concentrations vary across the landscape. The results form contour maps of invisible presence, like topographic maps, but for breadth instead of height. Carbon dioxide is especially interesting because it can travel through rock more easily than many other gases. It does not dissolve in water as readily under shallow conditions, so it may rise directly through soil. In some volcanic regions, CO2 emissions spread across broad zones rather than single vents. A wide whisper instead of a narrow one. Because carbon dioxide has no smell and no color, instruments are essential. You cannot rely on your senses. But with sensors, patterns appear, background levels, seasonal variations, localized increases. Again, it is not the single measurement that matters most, but the change in pattern. Sulfur dioxide, by contrast, is often more directly associated with magma nearing the surface, because it comes from sulfur dissolved in melt. When SO2 emissions increase significantly at certain volcanoes, scientists pay closer attention. Not with alarm, with focus. Focus is calm attention extended over time. Some monitoring stations continuously measure gas output from fumaroles and vents, transmitting data in real time. Others collect periodic samples that are later analyzed in laboratories with sensitive instruments that separate and quantify each component. Ratios between gases can be especially informative. For example, the balance between carbon dioxide and sulfur dioxide can suggest depth changes in gas sources. Ratios are like harmonies, relationships between notes. You imagine a mixing board where different sliders represent different gases. The overall sound depends not just on how loud one slider is, but how they compare. A shift in balance can be more meaningful than a rise in one alone. There are even satellites that can detect certain volcanic gases from space, especially sulfur dioxide in large plumes. They scan the atmosphere and identify spectral signatures, mapping drifting clouds across regions. From orbit, invisible emissions become visible patterns. Breath becomes brushstroke. You rest with the gentleness of this idea that the planet communicates chemically as well as physically. That composition itself carries information. That invisible things can still be measured, mapped, understood. Most of the time, volcanic gas release is steady and low. A background exhale. Life continues around it, plants grow, animals pass, weather moves through. Monitoring does not assume danger. Monitoring establishes normal. Normal is the anchor point of calm interpretation. You take a slow breath of your own now, noticing how natural it feels to exchange gases with the world: oxygen in, carbon dioxide out. You are part of this planetary chemistry, this continuous cycling. The difference is only scale and pathway. And as gases rise, they often pass through another traveler: underground water, dissolving, reacting, changing character along the way. Which brings a soft new curiosity forward: what stories might water be carrying upward from the deep stone below? You let your thoughts flow now, like water finding its path through soil and stone. Not rushing, not forced. Just guided by gravity and space and time. Beneath the surface of the earth, water is almost always moving somewhere, slipping through pores, tracing fractures, resting in hidden reservoirs. Underground water is a traveler and a witness. Rain falls, seeps into the ground, and begins a slow descent. Some of it pauses in shallow layers. Some journeys deeper, meeting warmer rock, meeting gases, meeting minerals waiting to dissolve. Along the way, the water changes. It gathers a chemical memory of every place it has touched. You can think of it as a letter carrier moving through many towns, collecting postmarks. In volcanic and geothermal regions, this traveling water becomes especially informative. Heat warms it. Gases mix into it. New minerals dissolve into it. By the time it returns to the surface as a spring, a seep, a bubbling pool, or a warm stream, it carries a story written in chemistry. Scientists read this story gently. They collect water samples from springs, wells, crater lakes, and runoff channels. The sampling itself is simple and careful: a clean container, a steady hand, a precise label. The complexity comes later, in the laboratory, where instruments measure dissolved ions, gases, isotopes, and trace elements with extraordinary sensitivity. Each dissolved substance is like a word. There may be more sulfate, suggesting sulfur gases mixed in below. More chloride, hinting at deeper hydrothermal fluids. More dissolved carbon, pointing toward magmatic gas input. Temperature affects how much rock dissolves, so warmer pathways often produce richer mineral signatures. You imagine water moving through warm stone like tea through leaves, carrying flavor outward. Acidity is another important signal. Pure rainwater is slightly acidic already, but volcanic gases such as carbon dioxide and sulfur dioxide can make groundwater more acidic when they dissolve. This shifts the pH, a measure of how acidic or basic a solution is, sometimes only a little, sometimes more noticeably. pH is like mood for water. Small shifts can indicate changing gas input below. Scientists track these changes over time, building records of what is typical for each spring or lake. Again, the baseline matters. Normal first. Then variation. Some volcanic lakes are monitored with special care because they sit directly above active systems. Their temperature, chemistry, and water level can change as underground heat and gas flow change. Instruments may float or sit along the shore, quietly recording conditions day and night. A lake becomes a window instead of a mirror. You picture a still crater lake under a gray-blue sky. It looks calm, reflective, silent. But beneath it, warm fluids may be entering from below, adding heat and dissolved materials. Tiny bubbles may rise. Subtle convection currents may circulate. The surface hides motion, but measurement reveals it. There are also gases dissolved in water that can be measured when samples are sealed and analyzed. The types and ratios of these gases, carbon dioxide, helium, radon, and others, can help estimate how deep the fluids traveled and what they contacted along the way. Depth leaves a fingerprint. Even isotopes, slight variations of the same element with different atomic weights, can be measured to trace origin. Certain isotope ratios suggest magmatic sources. Others suggest shallow groundwater. It is like distinguishing dialects within the same language. You rest with how delicate this science is. No explosions. No drama. Just careful sampling and patient comparison. In some places, long pipes are placed into wells so sensors can continuously monitor temperature, pressure, and chemistry at depth. Data flows upward through cables instead of buckets. Streams of numbers replace occasional snapshots. Continuity deepens understanding. Continuous listening is softer than occasional checking. Water levels themselves can also respond to underground changes. Pressure shifts can raise or lower groundwater in wells by small amounts. Sensitive pressure sensors detect these movements: slow rises, gradual falls, sometimes linked to seismic or magmatic adjustments. A well becomes a quiet gauge of hidden force. You imagine rows of wells across a volcanic region, each like a vertical listening tube placed into the earth. Not forcing answers, simply receiving them. Over time, patterns appear: seasonal recharge from rain, longer cycles of pressure, small anomalies that invite closer study. Water is especially valuable as an indicator because it connects systems. It touches rock, heat, and gas. It moves between them. It integrates signals. A single drop may have traveled through fractures kilometers deep before returning to daylight. Integration brings perspective. You feel a sense of calm respect for this, that the planet allows itself to be understood through such gentle means. That instead of needing to break or burn, scientists can learn by sampling, measuring, comparing. Curiosity expressed through care. Even the sound of water can be monitored. In some geothermal areas, subtle acoustic sensors listen to fluid movement in pipes and vents: soft gurgles, faint roars, delicate turbulence. Flow has a voice when you amplify it enough. Stone and water making quiet music together. You let that image settle: a hidden orchestra beneath the ground, playing in slow motion, each instrument a process, each note a measurement. Chemistry, temperature, pressure, sound, all blending into a readable composition. And as your thoughts drift upward again, following evaporating water and rising vapor, you feel another gentle question forming: if so many signals can be gathered from the ground in springs, what wider patterns become visible when we watch from far above the earth itself? You let yourself rise now, beyond the trees, the mountains, and even the clouds, floating into quiet space above the earth. From this height, the planet appears as a calm, curved expanse, a living map of colors and textures, rhythms and contours. It is still, yet not frozen. Subtle movements continue even here, unhurried and persistent, beneath your gaze. From orbit, nothing needs to be touched. Observation itself is gentle. Satellites drift along paths charted by careful engineers. They carry instruments designed to sense light, heat, shape, and motion. Some watch invisible light, capturing images like photographs. Others measure infrared radiation, revealing warmth patterns across the surface. Some send radar pulses, bouncing them off the ground to measure tiny changes in elevation. All are eyes in orbit, patient and silent. Radar imaging is especially remarkable. Unlike visible light, radar does not rely on sunlight. It can peer through clouds, rain, or darkness, returning precise measurements of ground position. When these signals are repeated over days and weeks, scientists compare the results, noticing movements of mere millimeters. What seems like stillness from the ground suddenly reveals itself as subtle uplift, slight subsidence, or slow tilting. You imagine the Earth breathing, a chest rising and falling imperceptibly, while satellites trace each curve with unwavering attention. Thermal infrared sensors complement radar by capturing warmth across the landscape. Dark volcanic basins may retain heat longer than surrounding areas. Hydrothermal fields emit gentle infrared glows, revealing the slow circulation of fluids beneath the surface. By watching repeated passes over time, scientists notice trends: zones warming slightly, cooling gradually, or remaining steady. Continuous observation is a form of calm vigilance. Satellites also provide high-resolution imagery for deformation analysis. Photographs of the same volcanic regions, taken from multiple angles and at different times, can be stacked to reveal how features shift. Mountains tilt fractionally. Valleys broaden slowly. Craters deepen imperceptibly. These changes are not abrupt catastrophes. They are long arcs of natural adjustment, recorded without haste, interpreted with care. You sense a quiet rhythm in this data, like a heartbeat stretched over days and months, a slow pulse of the Earth itself. Beyond mapping shapes and temperatures, orbiting instruments can measure atmospheric gases. Some detect sulfur dioxide plumes rising from volcanic vents. Others track carbon dioxide or water vapor drifting upward, connecting the ground with the sky. These measurements, integrated with ground-based readings, create a layered understanding of activity, a harmonious symphony of signals from multiple vantage points. Perspective grows as distance increases. You feel a sense of patience in orbit. The satellites do not rush. They repeat the same paths, scan the same spots, and steadily gather data. Day after day, month after month, the planet is recorded in its natural tempo. No alarms are necessary, consistency becomes reassurance. Patterns emerge quietly, without urgency. This long-term watching is a gift. It shows not only sudden changes but also subtle trends, uplift over years, gradual shifts in hydrothermal areas, slowly evolving thermal anomalies. By seeing these motions unfold, scientists gain context, separating fleeting anomalies from genuine geological shifts. You imagine looking at a time-lapse created from years of satellite images. Mountains gently swell, valleys gently settle, thermal patches appear and fade, streams shift course imperceptibly, and lakes expand and contract. All movements are soft, deliberate, and instructive. The planet is communicating its story in calm gestures, not in abrupt outbursts. Satellites can also help triangulate ground movements when combined with GPS measurements. Radar interferometry and GPS complement each other. One provides wide coverage, the other precise local positions. Together, they produce a layered map of land motion, more complete than either alone. Observation becomes collaboration, a gentle conversation between instruments and the Earth. Even the smallest shifts, once invisible to human eyes, now become readable. From orbit, you feel a connection to Earth's slow processes, understanding that change is ongoing yet rarely immediate. The planet moves at a different rhythm, one that is long, quiet, and reassuring once you learn to watch without rushing. From this height, you also see relationships, how a hydrothermal field aligns with a slowly rising caldera floor, how gas emissions correlate with gentle thermal anomalies, how subtle deformation mirrors unseen magma movement beneath the surface. Connections emerge, forming a tapestry of insights, each thread soft and deliberate, each color revealing part of the story. You sense the patience of science mirrored in the patience of nature. No reaction is forced. No hasty conclusions are drawn. Observation itself is meditative, a slow unfolding of understanding. And as you drift further into the calm orbit, you begin to wonder if we can watch from above and below, tracing shape, heat, and gases. How do we interpret all these signals together, to perceive patterns that hint at future whispers from the deep Earth? You settle into the idea that the Earth speaks in many languages at once, vibrations through rock, warmth through stone, gases through the air, water flowing beneath your feet. Each is a voice, each a signal. Alone, a single signal is a whisper. Together, they form patterns, melodies that repeat, change, and sometimes harmonize. Patterns are the calm structure of understanding. You imagine sitting in a quiet room, listening to rain tapping on a window. The first drops arrive sporadically. At first, it seems random. Then a rhythm emerges, a soft cadence, a gentle repetition. You begin to anticipate the next drop. Not because you know exactly when it will fall, but because you notice the shape of the pattern forming. Earth behaves in the same way, and scientists are the attentive listeners. Signals arrive from many instruments. Seismometers record microquakes. GPS stations track millimeter movements. Thermal sensors record subtle heat changes. Gas monitors detect shifts in composition. Water chemistry sensors register tiny adjustments in springs and lakes. Each line of data is a note. Each reading is soft pulse. Alone, a note is just sound. Together, they are a composition. Over time, the melody reveals itself. Patterns can emerge as clusters of micro-earthquakes, like a staccato rhythm. Ground uplift appears in repeated arcs, like gentle crescendos. Thermal signals rise and fall, blending with chemical whispers from gas and water. Observing one instrument alone is like hearing a single violin. Observing many creates a full orchestra. The score becomes visible only through careful attention over days, months, and years. You sense the patience in this work. Nothing is rushed. Scientists do not aim to predict every movement. They do not claim to hear the Earth's ultimate intentions. Instead, they identify tendencies, probabilities, and signals of change. A pattern may suggest magma is moving upward. Another may indicate fluid pressure is adjusting. These are not guarantees, but invitations to look closer, to listen more attentively. Prediction in this context is gentle. Probabilities are framed like moods, a landscape of possibility rather than certainty. Imagine a weather map. A shaded area indicates a higher chance of rain, but not that it will rain for sure. Scientists interpret geological patterns similarly. They watch for signs that are unusual or diverge from the long-term background rhythm. This requires context. Historical records, long-term observations, and previous eruptions create a baseline of normal. Deviations from normal are noticed, but not feared. The Earth has rhythms, and these rhythms are often slow and patient. A sudden tremor may seem dramatic to a casual observer, but within context, it may be part of a gentle, repeating sequence. Understanding context is like hearing the difference between a single drumbeat and a recurring drum pattern in a quiet composition. Even anomalies are interpreted softly. A new cluster of gas emissions or thermal changes may signal adjustment within the system rather than an immediate eruption. The goal is to understand the processes, to read the planet's language, not to incite alarm. Each signal is weighed alongside others, cross-referenced, and compared over time. The Earth offers hints, not orders. The beauty of patterns lies in repetition. When signals repeat, they reassure. When they shift, they invite curiosity. You imagine lines on graphs, colored bands on maps, waves of heat and gas plotted over time, all forming interwoven sequences. Some sequences may echo each other across years. Some may emerge suddenly. Each is interpreted with calm, attentive reasoning, like reading subtle gestures in a slow dance. Data becomes more than numbers, it becomes a living tapestry. Every instrument, every measurement, every observation contributes a thread. Seismic tremors are woven with ground deformation. Gas emissions intertwine with thermal patterns. Water chemistry adds its delicate shades. Together, they form an intricate and evolving picture of a deep, hidden system, a system that does not demand to be feared, but invites to be understood. You notice the soft humility in this work. Even with decades of observation, scientists cannot claim absolute foresight. There is always uncertainty. Some signals may conflict. Some patterns may surprise. But uncertainty does not mean ignorance, it means attentiveness, openness, and patience. Accepting uncertainty is a quiet form of wisdom, a way of harmonizing with Earth's rhythms rather than imposing human expectations on them. Patterns guide gently, like lanterns illuminating a foggy path. They hint, they suggest, they indicate possibilities. They never dictate with certainty. And in that gentle guidance, there is reassurance that knowledge does not always require control, that observation can be calm, and that the deepest understanding comes from sustained attention, not urgent reaction. And as you follow the interplay of tremors, heat, gases, and water, a new reflection begins to form if patterns can guide attention. What happens when the instruments themselves disagree, sending different signals about the same slow, hidden processes? You take a slow, deep breath and consider something quiet but profound. Even with the most sensitive instruments, the earth does not always speak clearly. Signals sometimes disagree. One sensor may detect slight uplift, while another nearby shows stability. Gas readings may rise in one vent but remain steady elsewhere. Thermal patterns may hint at change, while deformation appears minimal. At first, this seems confusing. You imagine hearing two friends describe the same sunset. One notices the deep reds and oranges, while the other notices the gentle violet streaks. Neither is wrong. Each perceives a different part of the whole. The same is true for monitoring Earth's hidden systems. Each instrument has a perspective, a voice in the chorus of observation. Seismometers, GPS stations, thermal sensors, gas analyzers, water monitors, each ear listens differently. A seismometer is attuned to vibration, but it cannot detect chemical composition. A gas analyzer senses changes in CO2 or sulfur dioxide, but it does not feel pressure in rock. A thermal camera maps surface warmth, but it cannot sense subtle subsurface deformation. Each instrument offers a unique lens, a singular way of listening to the Earth's subtle language. Disagreement is natural, not problematic. When readings diverge, scientists do not panic. Instead, they treat it as a clue, an invitation to explore why. They compare, cross-reference, and ask questions. One instrument might be affected by local conditions. Another might capture a delayed signal. Differences reveal complexity, not contradiction. The Earth is not simple, and careful observation honors that complexity. You imagine a room full of softly glowing screens, each displaying lines, colors, and numbers. Scientists sit quietly, comparing patterns, noting anomalies, and seeking context. They do not rush. They do not assume a single reading is definitive. They see signals as conversations, sometimes overlapping, sometimes speaking at different times. Multiple instruments together form a fuller picture. Cross-checking measurements is like using all your senses to understand a single experience. When your eyes and ears and touch all register the same sensation, you feel confident. When one sense differs, you pay closer attention, learning to interpret subtle cues. In the same way, the Earth's signals are cross-referenced to understand the larger system. You also notice that disagreement teaches patience. Not knowing everything immediately is not failure, it is part of learning. Instruments that differ encourage long-term observation and careful comparison. Patterns are sought across weeks, months, and years. Only by letting data accumulate can scientists see the forest instead of focusing on individual trees. Even in conflict, there is beauty. Imagine a symphony where one instrument plays a note slightly off the main melody. It draws attention, not chaos. It invites listening, reflection, and adjustment. Disagreement among instruments works similarly. It highlights areas that need more study, reveals subtleties, and deepens understanding. Calibration and context become essential. Every instrument has limits and sensitivities. Understanding its range and potential sources of error is part of the work. Scientists do not ignore discrepancies, they study them, adjust for them, and learn from them. Over time, the ensemble of instruments grows more coherent, revealing patterns that were hidden in apparent disagreement. You feel a gentle reassurance in this process. Science does not promise absolute certainty. Instead, it offers careful attention, repeated observation, and contextual understanding. By accepting that some questions cannot be answered immediately, you learn to rest with ambiguity, recognizing it as an integral part of the story. Even silence, after all, is a signal. When instruments are quiet, or when they speak differently, it is not a failure, it is an invitation to look deeper, to notice the subtle harmonies and rhythms that might otherwise be overlooked. Patience allows the discrepancies to make sense, revealing a more nuanced understanding of the hidden forces below. You imagine an orchestra again, instruments tuning, some slightly off, some in perfect pitch. The music is not chaotic, it is alive. Attention, practice, and observation gradually bring harmony. Scientific instruments are like that orchestra, each voice matters, each note contributes, and understanding emerges slowly, beautifully, and carefully. And as you rest with this thought, another curiosity forms. If disagreement can guide attention, what might the next generation of tools and networks reveal, quietly listening to the deep earth with even greater care? You allow yourself to drift into the possibilities of the future, imagining instruments that do not only record, but understand, instruments that watch without urgency and listen without distraction. The planet continues its quiet motions, and now your perspective includes the innovations that make long-term observation more subtle, more continuous, and more integrated. Artificial intelligence is among the quiet new companions. AI does not leap to conclusions. It does not rush. Instead, it sifts through vast streams of data, detecting gentle patterns that may escape immediate human attention. Small tremors, minor thermal changes, slight shifts in gas composition, each is registered, contextualized, and interpreted with calm precision. AI becomes a patient librarian, cataloging every signal and comparing it to past experience. Dense networks of sensors blanket volcanic regions like a soft quilt. No single station carries the weight of observation alone. Thousands of tiny instruments, seismic, thermal, gas, deformation, communicate continuously, sharing data in real time. Each sensor is modest, but together they create a comprehensive listening system, mapping the invisible rhythms of magma and fluids with an intimacy previously unimaginable. You imagine a grid of softly glowing points, each one connected invisibly, each one awake to the subtle motions below. The Earth's quiet sighs are heard everywhere at once. Monitoring becomes more than detection, it becomes presence. The act of continuous observation is like watching a slow sunrise. You are aware of the first hints of light, the gradual lifting of color, the unfolding of warmth. There is no rush. You watch to understand, not to react. Patterns are appreciated in their own time, insights accumulated gently over days, months, and years. Human curiosity itself takes on a calm form. Scientists, engineers, and observers are no longer solely seeking signs of danger. They are stewards, caretakers of knowledge, devoted to understanding the Earth's inner life. Their curiosity is patient, measured, and respectful. Observation is a practice of presence, a meditation on the slow, hidden workings beneath our feet. Data becomes an ongoing dialogue. Sensors transmit streams of information. Algorithms detect deviations from long-term baselines. Scientists review and interpret, connecting threads across time and space. Each new insight is not a shock, but part of a larger understanding. Observation, interpretation, and context work together, forming a tapestry of quiet comprehension. You imagine satellites orbiting with soft persistence, reading deformation, thermal anomalies, and gas signatures day after day, night after night. Ground-based instruments join in, like attentive friends positioned across the landscape. Together, they maintain a continuous, patient watch. The future also promises even more refined instruments, ones that can detect previously imperceptible signals, track subtle chemical changes, and sense motion with unprecedented precision. Miniaturized sensors could sit unobtrusively in volcanic regions, continuously learning and reporting. These are not intrusive tools. They are companions, quietly recording and relaying, always patient, never hurried. AI and dense networks will not replace human care. They will augment it. They free curiosity from routine measurement, allowing minds to explore interpretation, to notice subtle correlations, to imagine long-term possibilities without fear. Observation becomes a shared act of understanding, not a frantic effort to prevent disaster. You rest in the realization that Earth is watched with calm vigilance. It is not fear that motivates this work, but care. It is a gentle stewardship that allows the planet to reveal its rhythms, its messages, its subtle shifts, without coercion. Observation is a conversation, not a command. Understanding grows slowly, richly, and patiently. You breathe slowly and notice how this perspective transforms worry into calm curiosity. Each sensor, each satellite, each instrument is a silent friend, attentive and precise. Each signal is respected, each anomaly studied gently, each pattern appreciated in context. The Earth is not being forced to reveal itself. It is being listened to with patience. And as you imagine this quiet network of knowledge stretching across the globe, you feel a deep peace, a recognition that the deep Earth, with all its power and mystery, is met not with alarm, but with thoughtful, respectful, continuous attention. The planet is observed, understood, and cherished, and in that watching, there is profound reassurance. Above all, you rest in the comforting thought that the Earth's secrets are not sought in haste, but welcomed softly, one careful observation at a time, like a whispered story told slowly across the ages. And as this realization settles in, your mind drifts toward wonder once more what future discoveries will emerge from such gentle listening, as science continues to watch, learn, and understand the deep rhythms of our living planet.